All right, we are recording. So I will hand over the floor to Group 16 to share with us their uh, microbioincubator design.
All right, wonderful. Hello, everyone, and welcome. We are Group 16, and we are excited to share with you our novel design for the Tribio Autoreactor. I'm Ellie Scott.
I'm Peter Bukowski.
I'm Christian Garcia.
I'm Andres Orta.
I'm Uriel Ostrowicz.
I'm Griffin Schobel.
I'm Andrew Tomlin.
Okay, so first we have a quick outline of our presentation. We will be starting with reviewing our Hedgehog concept, following into a product overview and theory of operation. Then we have a subsystem analysis and technology readiness level analysis, finishing up with product expenses, and finally ending with a summary. So for our Hedgehog concept first. As you can see, our Hedgehog concept is the Tribio autoreactor can perform 3 separate experiments simultaneously by combining the capabilities of 4 standalone machines that are currently needed for bacterial culturing within one autonomous system.
All right, so now we are going to go into an overview of our products, looking at the individual subsystems that compose it. So first, for an overview, so our autoreactor is 55 inches wide, 24 inches in depth, and 40 inches tall. It weighs approximately 190 pounds, is composed of 3,638 parts, and contains 3 independent modular culture components. So now we're just going to go through each subsystem. And as we go through the subsystems, we're going to have listed the customer needs that each subsystem addresses. So for our housing subsystem, we have our housing is made out of 80-20 extrusions to make the housing rigid, and this also adds modularity to design if the customer desires to add things in the future. Our door uses friction hinges, so that way the door stays open while the user is accessing the inside. And when our door is closed, it activates a limit switch. And now this is a safety precaution that we have in place to ensure that there's no harm done to the user when the gantry is running or anything. So when the door is closed, everything inside, all the dynamic systems will not move. And then as you can see on the picture of our left, we also have a polyvinyl fabric cover to protect experiments from the photo-bleaching effect and not interfere with any fluorescent intensity or optical density measurements. And this is a really nice, cheap option that's easy to sanitize in a laboratory setting. So for our gantry subsystem, we based our gantry used mostly in like 3D printers. So for our X and Y movement, we use primarily belts. And for our Z direction, we use a lead screw. And the gantry contains limit switches in each direction of motion in order to obtain closed loop control of the system. And this allows for our accurate and precise movement of our liquid handling subsystem. So for liquid handling, we use an Opentron's electronic pipette, and this product was chosen mostly due to its ejector mechanism. So it can automatically dispose of its tip into a waste container and retrieve another tip. So as you can see here on the left, we have a green compartment with 384 sanitized pipette tips. So this liquid handling system would actually be able to eject its tip and get a new one with no risk, reducing the risk of cross-contamination occurring between well plates or tubes or between compartments. So for our culture modules, this is actually where the experiments will be taking place. So we have acrylic tops to allow fluorescent intensity and optical density measurements to be taken without opening the module. The module is sealed with magnetic gaskets, similar to the ones used often in refrigerators to ensure a tight and proper seal. And we have on the inside harsh environment limit switches to ensure the experiment cannot be ran while the module is open. They can only be run while the module is closed. For our environmental control, as you can see down here, we have ports for each gas. We have methane, nitrogen, hydrogen, carbon dioxide, and oxygen. Now it's really important. We have our oxygen line separate and away from everything else. We even have it labeled differently in red. Oxygen is separated for the other gases to ensure safety, and the oxygen line that we have has brass fittings to eliminate risk of any combustion that may occur. Now, each line has a flow rate sensor to know the flow rate of gas entering each compartment. It has solenoid valves to allow the user to control gases entering each compartment, allowing for each compartment to have unique atmospheric conditions. We have check valves to use to ensure no gas backflow occurs from the actual modules back into the gas lines. And then we also have vacuum pumps that are used to evacuate the gases to store them at any location desired by the customer later. So now for our shaker system. So the motors used for the shaker use integrated absolute encoders, and this allows us to know their position anywhere in Euclidean space. So for achieving linear motion, we use a motor attached to a crank arm and a unibearing. When this motor runs, we will get purely linear motion. For achieving orbital motion, we have a motor attached to the underside of the well plate platform, and running this motor gives us purely orbital motion. Now, each motor has a crank size of 1/2 inch. So with a combination of running both of these motors, we can achieve double orbital motion with our design. And then each one of these shaker systems is in each module, giving you independent shaking patterns can be obtained for every single experiment and module. For temperature control, so we use multi-stage Peltier plates that heat each well plate or two via conduction. And as you can see down here, we have a heat sink on the underside of the Peltier plates and a fan in the module to dissipate any unwanted heat. So for our fluorescent intensity and optical density sensors, we use a laser mounted on the gantry. And we have independent mounting configurations of PCB boards with photodiodes for well plates and conical tubes, which we will go into more detail of how this subsystem works a little bit later in the presentation. So for our user interface, we have a USB port on the back of the device to allow for a computer to be plugged in and to interface with the device directly. So with this, with your computer, you can monitor culture conditions directly. You can program any operations that you want. And on the front of the device, we have an emergency stop button, similar to the ones used in CNC machines. So you must twist and push this button to be able to like stop all operations within the device. And this was done just for, in case no one accidentally bumps into the button, stopping the machine accidentally within like the laboratory. We also have an AC to DC converter within the machine, allowing us to operate out of a standard 120 volt outlet. And then the whole entire machine is it is a Raspberry Pi is used to handle the computing and closed loop control of the entire system.
Okay, so now we're going to go over a theory of operation to figure out how all these subsystems come together to perform the functions needed for our customer. So as you can see in the model on the left, it's the clear look of it. In reality, it would have the polyvinyl black coverings as stated previously. This is just for clarity. But basically to conduct an experiment, the user is going to have to manually open up the door, and it's going to rest high due to the friction hinges. So they won't have to worry about the door falling and making contact with them as they're inputting the given well plates or conical tubes into our system. So also, as previously stated, there are 3 independent culture modules. So the first step is the user essentially placing either the well plate or the conical tubes within each culture module. And to do so, they'll just have to manually remove the lid that goes on top of each culture module. Once that lid's removed, they have essentially 3 categories of choices. They have inputting a well plate, a 50 milliliter conical tube, or a 15 milliliter conical tube into the shaker plate. So on the left is a configuration using well plates, and more specifically, it's a 384 well plate. One of the customer requirements was being able to run different types of well plates, ranging from 6 well plates to 384. So this is just an example of a 384 well plate that has an aluminum perforated sheet metal piece that is used for temperature control, which we'll go into a little bit more detail later. But basically that's able to plug into the shaker plate as shown. On the other side, you have the conical tubes, and they're essentially in conical sets, I would say. So for the 50 milliliter case, you have 3 of them that can be in a configuration. And for the 15 milliliter case, you have 5 that can be in a configuration. They look a little different than how it's structured on the left for the well plates. And that's due to how the fluorescent intensity and optical density are measured. And we'll get into that a little bit later. But those essentially press into the shaker plate, whereas with the well plates, they plug in. Okay, so once the user has put in the well plate or conical tube, it's time to load the electric pipette. So what's going to happen is we wanted to be able to satisfy the condition of needing to have 384 nozzles in use based on the 384 well plate criterion. So we have a 3D printed cavity that is able to house 384 disposable pipette tips that are rated for 100 or 1000 microliters. So what happens is, since the fluid handling system, the open trans pipette, is mounted on our z-axis, it's able to move down to where the nozzle cavity is, and they're able to press in and pick up one of the disposable nozzle tips. So once the nozzle tip is loaded, it's able to move to the module compartments. So once inside the culture modules, what happens is the user is able to add the fluid of interest they want inserted into either the well plates or the conical tubes. So as can be seen on the left image, there's a turquoise colored cup, which is an off-the-shelf 235 milliliter fluid container. So since our maximum case is needing 150 milliliters for 3 sets of 50 milliliter conical tubes, this is more than enough fluid to ensure the user won't have to manually add a new cup in there of new fluid. But assuming it's the same fluid that's being added to each well plate or conical tube, only one nozzle will be needed to go back and forth between the well plate and the cup. However, once the experiment has been finished, if the user is interested in moving fluid from one module to another module, what they'll have to do is they'll have to go back and forth to the 3D printed cavity to ensure cross-contamination is not an issue. And the way we handle that is we have these plastic off-the-shelf containers that are located directly behind the modules. So once a tip has been finished for removing fluid, the fluid handling system moves to the back of the product and it ejects the tip into the container. Once an experiment is finished, the user is able to actually just pick up that container, take care of them how they would normally dispense them, and they'd be able to refill them in a new cavity block that they'll exchange with the empty one. So as previously stated, we're able to handle methane, nitrogen, hydrogen, carbon dioxide, and oxygen in these input ports. And so it's expected that the client or whoever in the lab, they have their own gas containers that they're able to route to these input ports. On the other side of the device, so in the bottom picture, we have 3 output ports, which the vacuum pumps in our atmosphere system, they're able to pump out the effluent gas after each compartment or each experiment is finished for each module. Okay, so now that everything's set up inside the culture module, we're able to basically press play, given the input of whether it's a well plate, a conical tube, and what size well plate. So in each compartment, we're going to be able to have our own shaking patterns, as stated, linear, double orbital, or orbital. We'll have our own atmospheric conditions, and we'll have our own heating conditions for each module. So in the event that the user finds something wrong in the experiment, they're able to press the e-stop button, which is conveniently located at the front of the device. They have to turn it and press it, and that'll stop operation if anything is going wrong. All right, so as the experiment is running, the user is able to measure fluorescent intensity and optical density. And it's done a little differently depending on whether you have a well plate or a conical tube. So we'll start with the well plate, which is on the right. As stated previously, it'll involve a custom PCB board that has 384 silicon photodiodes. Those photodiodes are spaced 4 millimeters apart. And given the small size of those photodiodes, each one is able to fit within a 3 millimeter diameter of perforated aluminum that goes around the 384 well plate. So what's cool about that is if I want to move down to a 6 well plate or something that's less than 384, there's always going to be a photodiode that is located within the range of the laser moving through it. So depending on whether it's 6 or 384 in that range, the photodiodes are going to be able to receive the laser intensity from our laser. The laser 2 is a 640 nanometer laser, so it's red. And it's located at the bottom of our z-axis. We'll go into a little bit more details in our analysis about maintaining the intensity needed to calculate optical density based on our customer requirements. So then for the conical tubes, it works a little differently. We can't shine it directly through, given that we have conduction occurring through our Peltier plates. So what we have to do for this is we have to shine a laser at a 45-degree angle from a mirror. So as can be seen, the laser will shine, make contact with the mirror, and through these machined holes in our aluminum housings, similar to how we're doing it for the well plates, we're going to be able to read fluorescent intensity and optical density. Okay, so to verify some of the customer requirements and functionality, we're going to go over a little bit of subsystem analysis. So the first thing regarding the shaker system, it was asking we needed linear, orbital, and double orbital motion. So a SolidWorks rigid body dynamic analysis was performed to verify the motor torques and the different type of motion. So as can be seen on the left, there is there's a plot showcasing the trajectory of a given well plate. So with a constant crank arm radius of 1/2 inch, it gives you like a 1/2 inch orbit, as you can see. And it was found that we would need a torque of 0.7 pound-inches to run at an RPM of 300, to run at 300 RPM, which was deemed as an optimal shaking speed for bacteria. The motors selected are NEMA 17 motors that come from CUI devices. And those motors, they're able to handle from 150 RPM to 900 RPM with the given load. So the user has a lot of choice in selecting the shaking speeds. So if we move on to the next slide, you can see it's a very similar calculation for the linear pattern, where we're going to need 0.9 pound-inches to get the necessary motion for 300 RPM. The plot on the left, it's linear. The y-axis, it's pretty much the same value. So you still have that 1 inch of oscillation. And if we go forward to the double orbital analysis, you can see when you run the orbital motor at 180 degrees out of phase, you're going to get double orbital motion, as can be seen in the rigid body dynamic analysis plot. And similarly, the torques were calculated for this RPM. And the reason they're a little bit higher for one of the motors is the change in your moment of inertia as it's rotating through space. So basically, our motors are spec'd out to handle those different shaking patterns. Another thing that was important is, given that we have the shaking, is to make sure that the material we selected for our base plate, we're able to avoid any critical natural frequencies that would cause unwanted shaking or unwanted oscillation in our device. So a modal analysis was conducted in ANSYS based on the base plate and the types of loads that would be on this plate. So in the sections that are red, there was a max deflection of around 3/4 of an inch. And given that everything is operated on a gantry system, we need to know where everything is in Euclidean space. So we don't want a crazy deflection like 3/4 of an inch when performing our pattern. So then if we go into a little bit of structural analysis, this was just quick to verify that the base plate we did select would be fine as far as those deflections. So applying the loads of everything that was existing on the plate, we saw that we'd have a deflection of 5 thou, which is essentially negligible for our purposes. The safety factor was 64, so we knew our material selection and thickness of 6061 aluminum, 1/8 inch for our base plate was more than enough to satisfy our conditions.
Because there's a load acting on the lead screw from the electric pipette and sensors, a lead screw calculation needed to be performed. To ensure the lead screws could be rotated up and down, the motor torque required to rotate was calculated and was found to be 0.0128 Newton meters. The motor that we chose was a NEMA 17 stepper motor, which can achieve a torque of 0.5 Newton meters, which is far above the requirement. For the customer requirement of no creation of aerosols, it is important to ensure that the fluid is being dispensed using laminar flow, which occurs when the Reynolds number is below 2300. So using the geometry and properties of the Oppentron's pipette, the Reynolds number was calculated to be 6.74, well below the turbulent cutoff. It was required that the well plates and conical tubes must be able to reach temperatures of 4 degrees Celsius to 70 degrees Celsius. First, a 1D steady state heat transfer analysis was performed to verify each temperature could be maintained. For cooling, as long as the heat that can be removed, Q max, is above the heat that needs to be removed, Q remove, then temperature can be maintained. This is the case for both the cooling of the well plates and conical tubes, as shown in the slide. And for heating, as long as the temperature required by the Peltier plate due to the loss of heat to the air is lower than the max temperature that the Peltier plate can reach, then the temperature can be maintained. And as you can see again, this is the case for both the well plates and the conical tubes. So next, a transient analysis was performed to see how long the well plates and conical tubes would take to heat and cool to the maximum and minimum temperatures respectively. It was found that using a semi-infinite solid approximation with a constant boundary temperature, that the well plates take approximately 12.8 minutes to heat and 0.71 minutes to cool. The time the conical tubes take to heat and cool varied based upon the amount of fluid inside the conical tubes. At a worst case scenario, when the tubes are completely filled, it could take up to 4 hours to heat and cool. But if they're only filled partially, it could take as quick as 10 minutes. And lastly, we were required to achieve an intensity of 1 kilowatt per square centimeter with our laser. And so using a Gaussian beam approximation, we were able to choose a laser that with its inherent intensity and at a maximum distance of 27.13 centimeters, or approximately 1 foot, achieves that requirement.
We'll now be moving on to technology readiness levels for the subsystems that make up our product. Starting with the housing subsystem, we use commercial off-the-shelf components with proven technology in numerous real-world operations, including various framing and structural applications, proving to have very to little no risk and having the highest TRL level of 9 for this subsystem. As for the gantry, once again, we use commercial off-the-shelf components with a proven track record in the 3D printing and various other applications. Once again, having low risk and a TRL level of 9 for this subsystem as well. For the liquid handling subsystem, once again, we use commercial off-the-shelf components from Oppentrons, which is a proven commercial technology for autonomous liquid handling operations, showing once again low risk and a TRL level of 9. For the culture modules, we once again use commercial off-the-shelf components with proven technology in various operations with low risk. However, due to the criticality of the seal needed for a successful operation with the culture modules, we need to ensure that genuine gaskets and sealing materials are used and are not of counterfeit products. And we need to adhere to appropriate assembly and operation procedures to ensure appropriate application for our culture modules. However, with that in mind, TRL level will still be 9 for this subsystem. Moving on to the environmental control subsystem, once again using commercial off-the-shelf components such as various fittings, adapters, check valves, solenoid valves, and manifolds with a proven technology for all gas systems used in the marketplace today with little to no risk. However, when dealing with high pressure gases, as in which will be used here, need to adhere to proper safety protocol and not take for granted the technology at hand, especially when using oxygen, methane, and hydrogen gases in close proximity. However, the subsystem with technological readiness level will still be a level 9. Moving on to the shaker subsystem, once again using commercial off-the-shelf components with proven motor technology for linear and orbital motion operations. However, due to the novel approach we are using for double orbital motion, it has never been used before in the technological space, with only analytical studies performed as seen previously in our slide deck. With that in mind, we need appropriate testing and control software development needed for this, resulting in a TRL level of 2 or 3, depending upon your technological readiness level definition. As for temperature control, we once again use commercial off-the-shelf components, as in heat dissipation fins and Peltier plates, which are proven for heating and cooling and heat dissipation operations, proving to be low risk and with a TRL level of 9. With the fluorescence intensity and optical density sensors, once again use commercial off-the-shelf components as in the laser and the PCB board. However, within the realm of cell culturing, this is a novel approach to determine the fluorescence intensity and optical density, with previous benchtop machines used to determine these measurements. The technology does work, however, has not been tested in the cell culturing environment, resulting in a TRL level of 4 with progressing towards a TRL level of 5 in the cell culturing environment. And finally, moving on to the user interface and control software, we will be using commercial off-the-shelf components for the interface hardware, such as a USB port and a computer monitor, with this being common practice for user interfaces in the laboratory environment. However, this will be some risk moving forward in terms of the overall system control software. Due to our product transcending current technology is necessary for development of the control software to control the gantry, liquid handling subsystem, gas control, temperature control, shaking system, and the FI and OD measurements. With this in mind, we need further, we have developed a concept and application with further development needed for this subsystem, resulting in a TRL level of 2. And ultimately, this limits our technological maturity for the entire system moving forward.
All right, quickly moving through our product expenses. All right, so this is a chart showing our expenses for off-the-shelf parts, raw materials, manufacturing, and assembly labor. Our total cost comes out to be a little over $11,000, but this is a conservative estimate, rounding up for most values, including using a $58 recommended value for $58 an hour recommended value for the assembly labor. So quickly to justify the cost, we believe that this cost is entirely justified. Trivio can perform 3 separate experiments simultaneously, which saves the purchaser valuable time and lab space, as well as money instead of purchasing multiple products to do the same thing. Compared to other designs, both in our direct competitors as well as current technology, Trivio can perform more of the customer needs more efficiently. Trivio is also safer and incorporates redundancy both into the gas control system, which is where a lot of our cost comes from. This is to reduce the risk of unwanted gas mixing leading to combustion. And then finally, we have done quite a bit of in-depth analysis that has gone into our design justifications, meaning that we believe we have high viability and can justify that we have the best choices for all of our parts.
And now we'll go into a quick summary to close out the presentation. So we've introduced our product, its features, and our supporting analyses. And I'm sure you've seen many other product options for your needs. And having looked into them myself recently, I can certainly give them praise for their ingenuity. But the question still remains, why choose Trivio? Our product offers a high value proposition for your lab. We've integrated the processes of 4 existing lab devices into our one single product. These would be the shaker, the plate reader, the incubator, and the liquid handling systems. In a traditional lab environment, these devices would be manually interacted with, and the well plates would be physically transferred from one device to the next. With our device, human interaction is almost entirely eliminated. Due to the implementation of the 3 discrete testing chambers, our product is able to complete 3 processes in parallel under unique conditions. Since the modules have been isolated from each other, it's possible to test 3 unique cases simultaneously, being the different gas controls, different temperatures, and different shaking patterns. We've also performed first principle analyses on the system to prove its viability. As we've shown in detail earlier in this presentation, these analyses include heat transfer, dynamics, vibrations, fluids, and visual processing. And last, but certainly not least, we have multiple system redundancies to provide a safe user experience and reduce the possibility of experiment failure. In the case of emergency, there's a clearly visible and easily accessible emergency stop button on the front of the device. We have implemented brass fittings for the oxygen gas lines to reduce the risk of combustion. There are limit switches on the gantry, on the acrylic panels on top of the modules, and on the front door to ensure that no procedures can be run without the modules being closed or the door being closed. And we've also mitigated the chance of cross-contamination by fully enclosing the device and applying the disposable pipette tips used by the Alpentron dispenser. So knowing all this, we hope you find our product suitable to your needs and possibly choose it going forward in this process. We will now open the floor for questions. Thank you.
All right, great. Thanks, guys. So we've got about 10 minutes for Q&A. So we'll open it up to the panel.
So I'll start by saying, congratulations on like giving a walkthrough of sort of the concept of operations. It's the first time I've seen that. I really appreciate it. I think it really helps paint the picture of what your product is intended to do. I think you did a really good job with it. I wanted to ask, again, it seems like we're taking a really long time to heat and cool and that you're asymptoting to 70 degrees. I'm wondering, if your system is taking that long, why not add a little bit more power and have sort of a max temperature that exceeds that so you're not, coming up to an asymptote and taking so long? Is there some reason that you can't just put in more power?
Yes, there's a perfectly good explanation for this. The multi-stage Peltier plate that we're using, it is has a very high temperature differential already, and to find one that has an even higher temperature differential, the cross-sectional area that's exposed to the metal gets smaller and smaller, and the heat transfer becomes much less efficient. And
So
if
this
you
is
try,
sort of a limit of the technology.
right, exactly.
So what
And
happens if somebody cranks the temperature in the lab down to 65 degrees instead of 70 degrees? Are you going to be able to hit your 70-degree threshold?
yes,
You sure? Because if you can just barely hit it now, it seems like, if your ambient temperature goes down a little bit, that's going to be like almost a 1-for-1 on your high temperature.
that is true. It does take quite a bit of time to reach that high temperature for the conical tubes. But if we tried to switch the system to some other heating system, it would be much more expensive. And with this Peltier plate option, find that it's the most efficient for the cost. Keep it as close to the $10,000 as we can.
Okay. I mean, resistive heaters are pretty cheap. Where does the heat go? So you're sucking heat out of your system. Where does that heat go?
So there's a heat sink and on each shaker, and then there's also a fan in each shaker that will remove some of that heat that's coming, the excess heat that's coming off of the Peltier plate.
And where does it go? Is that enclosed in your box, or is that being dumped to the atmosphere?
It is being stored in the box, but eventually it will disperse through the walls and it will get into the atmosphere.
How hot is the box going to get before it does that?
The box should only reach maybe 30 degrees Celsius.
Well, I'm not so concerned about like the outside temperature of the box. It sounds like that'll be well within the limits. But if internally the box is getting warm, that's going to further reduce the efficiency of your heating or of your cooling.
That is true. But the heat will eventually be getting removed at the same rate that it's being supplied. And if there isn't enough heat that is being taken away from the well plates during the cooling process, then the temperature can be driven down even more if the fan speed is increased as well.
How sensitive are the cultures to the temperature? Do they have to maintain this at a certain temperature for a certain time, or like how long is their usual experiment process, I guess?
So we were told in our customer requirements, we would need to have a maximum case up to 2 weeks of constant operation.
Do they change temperature over that time? Is there like a cycle, or is it all one temperature?
We assumed it's constant parameters for each culture module. So in this case, it would be one temperature. That's why if we have the conical tubes, there would be a little bit of preheating or pre-cooling that would need to occur. So it would be difficult for us to change temperature really quickly if we had to do so for, say, the conical tubes. However, if we had to do it for well plates, it would be a little bit easier.
So just to follow up, I think Elise might be asking a slightly different question, which is if I could interpret is how long can the cells go at a non-ideal temperature before they get injured or damaged? I think Elise is what you're asking.
Yeah, that's a good question. Yeah.
That's I would say a biological requirement that we would need further clarification from the labs. That's not something that as mechanical engineers, we have direct intuition on.
Can you,
Sorry, one follow-up. I do believe commonly in a lab environment, the samples are produced at room temperature and then pushed to these extremities once they're put into like a bioreactor. Like it's not. I believe the point of the bioreactor is to test the limits and to force evolution.
Yeah, so I'm going to cheat a little bit because I know the number, but I think you could figure it out by just sort of thinking through what's done now, right? So at the moment, the situation you guys are trying to kind of beat with your product is they have 4 separate machines, right, that do each of these 4 different tasks. And a technician comes along and pulls a well tray out of one of the machines and walks it over to another machine, puts it in there, takes the measurement, pulls it out, walks it back over, and puts it in the first machine. So it's, and that's not great, but the cells don't die in that time period. So I think we're talking about the order of like minutes. So I would say like 10 minutes, 15 minutes at the max before things start to, before you're no better than just allowing a technician to do everything by hand, in which case, why spend $10,000 on this thing when you could just have a technician do it? So, and the number is about 15 minutes that we've gotten from the customers when we've asked. So, yeah, so in your heat transfer calculations is if you're exposing the cells to an environment that's not healthy for them for more than 15 minutes, that's probably something that needs to be looked at.
We meet that requirement for if you go to the previous slide or the following slide, that the well plates for heating up to 70 degrees is only in 12.8 minutes, and then cooling is also less than a minute. So for well plates, we do meet that criterion. It's only when the 50 milliliter tubes are filled to the very top do we reach these times that reach hours on end. But if as denoted by the 10-minute level there, if they are filled halfway for some of the volumes, we do also meet that requirement as well.
And so this stems from being able to change the temperature during an operation. So with the assumption that we could do preheating if we needed to move from one molecule to another, we'd be able to satisfy it. However, it wasn't in our requirements that we had to have modular temperatures within the cell filter.
All right.
I have one more quick question if we have the
Yeah,
time.
go for it. We've got about 2 minutes.
So first of all, I'd also like to say thanks for the theory of operation. That was great. Can you go to the shaker slide on the theory of operation, please?
This one, or the analysis,
One
or the
that
theory?
looks like the assembly. The one that looks like an assembly. Yeah, there. Okay, so is that a combination of off-the-shelf parts for that arm and cam kind of thing, or did you guys intend on making those?
That's correct. So for example, the clevis is an off-the-shelf part, all the hardware off the shelf. The only things that aren't off the shelf there are the dog bones. So that in case, like if you see at the linear motor, there's that aluminum piece that it's just 1/8" aluminum that would just have to be milled out. And the same thing directly under for the orbital shaking, there are also custom aluminum parts that you just press bearings into, flange bearings.
Okay. Sounds good. And when you put the well plate onto the thing, it's kind of shown better in one of the slides before, but there's like other clamps that aren't fasteners. What are those?
So that's since we have heat transfer flowing through, basically it's kind of like an aluminum sandwich that's encompassing our well plate. We want to reduce any form of thermal dissipation through the ambient air. So by having those, they're just 3D printed plugs that press, connecting the top sandwich piece, if you will, to the bottom sandwich piece. Whereas for the other 2 compartments, they're pressed into the cavity that's created.
Okay, gotcha. Okay, thanks.
No problem.
All right. So I think that's probably a good place to wrap up because we're just about a minute over time. So let me stop recording.